So what happens when the outcome of an experiment appears to contradict a theory? Well, there was an apparent contradiction of Newton's theory of gravity before he had even published it. A number of observatories were making very careful observations of the moons around Jupiter, particularly the inner moon Io. What you can see from the perspective of Earth as Io moves around Jupiter is that Io moves in front of Jupiter, it moves behind, and then it will pop out of Jupiter's shadow relatively quickly. So this is something that you can manage to time with a particular amount of accuracy. And this was very, very useful for observatories at this time because it was something that all observatories could observe at the same time so that they could synchronize their clocks. But there appeared to be something a little bit wrong with those timings. What they were seeing was that over a period of about a year or so, it looked as if the moons of Jupiter, specifically Io, were speeding up for around about 6 months and then gradually slowing down for about 6 months. Now, if this were true, then Newton's theory would be dead in the water. There's no way that Newton's theory of gravity can account for orbits speeding up and slowing down in this way. Was Newton's theory of gravity dead in the water, or can we find another explanation for this phenomenon? Let's look at it in a little bit more detail. I'm just going to draw a very simple diagram of the solar system, not to scale and not with all of the planets. So we have the sun in the middle, and then we have the Earth, which moves around the sun like this. So we'll just draw in the Earth here. And finally, quite a bit further away, we have the planet Jupiter. Jupiter is much bigger than the Earth, and it has lots of moons orbiting around it. We're going to concentrate on the moon Io. So Io moves around Jupiter in this way. So we're looking down on the solar system. We have the Earth moving around in an orbit around the sun here. We have Jupiter moving much, much more slowly around the sun here. And moving very quickly around Jupiter, we have the moon Io. What we observe is that the timing of Io coming out from behind the shadow of Jupiter is happening later and later and later than we expect. So does that mean that Io is actually travelling slower? Well, look what's happening to the Earth at that time. What the Earth is doing is it's moving around the sun, and it's actually moving away from Jupiter and Io. So we can find another explanation for the fact that as the Earth moves away from Jupiter, Io is moving more slowly, and as the Earth is moving through the other half of its orbit, Io appears to be moving more quickly. It's actually down to a finite speed of light. Light doesn't travel infinitely quickly. It takes quite a few hours to travel all the way from Jupiter. But what's more important is that for light to travel from one side of the Earth's orbit to the other, in other words, for it to travel this distance here, it takes about 16 minutes or so. So when we are at this point in the Earth's orbit, this event will appear to happen 16 minutes earlier than if we had seen the same event from over at this side of the Earth's orbit. So right the way back in the 17th century, people were able to deduce a finite speed of light and even get a rough idea of what the speed of light was. This is a pretty tricky concept, so feel free to draw your own diagram, maybe review the video, because we're going to be coming back to this idea quite a few times during the course. The key message here is that when we have a theory that we trust to some level, we can use it along with conflicting evidence to actually build up a more nuanced picture of the universe, a slightly more complicated way of looking at things. And we're actually going through this process with our theories of gravity at the moment. We have a little bit of a mystery. What we find is that when we take a galaxy and we add up all of the things that we can see which make up that galaxy, for example, the stars, gas, black holes, in fact, everything which is giving out radiation or blocking radiation, when we compare the mass of all of those things against the mass of the galaxy, which we calculate from the way things are moving, so using Newton's laws backwards to work out the mass of something from the way that they move, we find that they don't add up. And what we call this phenomenon is dark matter. And so the idea of dark matter is that there is other mass that we can't directly detect over and above these other things. And it actually makes up most of the mass in the universe. There are two possibilities. Either our current theory of gravity is wrong, which is meaning when we make our calculation of how much mass there is, we're getting the wrong answer. Or there really is a different kind of matter which we can't detect with current telescopes. Either of those possibilities are possible, and both of those possibilities are being actively explored. But the more observational evidence we get, the more it's pointing towards dark matter being a real phenomenon rather than just a small mistake in our gravitational theories. So this process of resolving ambiguities between our observations and our theories will allow us to discover new things, new theories of gravity, or more likely, a new type of matter that we haven't yet been able to detect.